Hi everyone, hope you're having a good day. Today, what I would like for you to do is complete this form on a separate sheet of paper. If you want to print it out from Canvas and then complete it on there, that's totally fine as well. It's your choice. And then I will walk you through, how to complete it on the next slide. So just give it a couple minutes and complete this warm up, and then we'll go through how to do it on the next page. Okay, so first you're just completing the table by listing all 10 samples of size 2. So they did the first one for us, Jocelyn and Elise. And so then we also have Jocelyn and Michael, Jocelyn and Erica, Jocelyn and Sarah. And then I just went down the list. Next, I did Elise first, and she was still needed to be paired with Michael, Erica, and Sarah. And then I did Michael, Erica, Michael, Sarah, and then Erica, Sarah. And then to find their average age, I just added their ages together and divided by 2. So that's where those numbers came from. And then the sampling distribution of the sample mean age is where you just plot all the means on a dot plot like this. And so you can see, kind of the general shape. For letter C, the mean of the sampling distribution of the sample mean it just means that I'm going to add up all these means, all these sample means, and find the mean of those. And so we use that symbol mu of x bar. It means the mean of all the sample means. And that equals 12.8. And then just mu by itself is population mean. That's the age of all 5 kids, the average age of all 5 kids. Number D is the sample mean unbiased estimator. Yes, because the mean of all the sample means equals the population mean. And so that is what that means. If it's unbiased, it means it's true when you find it. And then letter E, what if we had used sample size 3 instead of 2? Well, 3 is larger than 2. And so remember, as n increases, your variability decreases. So 8 and 17 wouldn't have been the min and the max. It would have been more concentrated on the inside. So hopefully you see how that kind of works. This is an example of a sampling distribution where we can actually see all possible samples of the same size from the population, because our population only had 5 people in it, and all possible samples were 2 at a time, and so we were able to calculate that there. Okay, so for your activity today, you're going to go to this website at the top of the page first for how to get your samples. And so you're going to do that. Well, actually, not until you get to number 2. And you're going to use that to do just, 2 and 3, 4, and 5. So if you're not in class, then you're not able to share your data with the rest of the class. But I still want you to do the act of going to the website and calculating the values so that you see what everyone else is doing. And then you can see the dot plots that we get together on the next page. And if you are in class, then we'll use the Statlet to collect everyone's data. All right, so pause here, complete the activity, and then we'll come back to go over the answers. All right, so let's start at the beginning. What type of probability do we have? We have checked our bins, binomial or binary, independent. Our sample size is 50, and our proportion probability of success is 0.4. And so it's a binomial distribution. These are mine that I did when I did this activity. I got 21, 14, 14, 19, and 16. So you guys would have gotten 5 different values. And then when we plot them all on the same dot plot, I had to use different method, but this is probably what our graph looks like. So we're going to label this as the sampling distribution of X, where X was the number of orange candies in 50 Reese's. And so I'm just going to circle this one right here. That is the number, or one sample of 50 Reese's pieces and the number of orange. And so that's why this is a sampling distribution of X, which is the number of orange candy. So it shows us possible samples of size 50 and possible outcomes for the number of orange candies. And so we used this formula for the mean. Mu of X is N times P. Sigma of X for standard deviation is square root NP. 1 minus P. Those are binomial formulas. And then we use the large counts condition to check our shape. Then we have approximately normal. And so that is stuff that we learned before winter break, but we are using it now. And so that's going to be really important to us as we keep going. Okay, so if you continue with the rest of the lesson, then you should have turned all of your samples, all of your orange candy numbers into proportions. And so that's going to be all values, or each value, divided by 50. I'm just going to use the divide symbol so we can know exactly what we did. And what that does is we're going to just look at this graph right here. Is it makes our graph exactly the same. Look at that. They're the exact same graph because all we did was take them and divide by 50. So I'm going to look at this 0.6 again. That one is one sample of 50 Reese's Pieces. And the proportion of orange. And so when we have a sample proportion, we call that a p hat. And that's going to be a sample proportion, or proportion from a sample. And so each of these little values are all little p hats. So this is called the sampling distribution, not of X, but of p hat. And so p hat equals X over N. Your X value, number of orange candies over your sample size, 50. And so that's what each of these are. These are all p hats. So that is there. And then to find the new mean and new standard deviation, what you guys did was you divided by 50. So I'm just going to show you a little algebra over here. We took N times P and then we divided it by N. And so the N canceled. And so the mean of all the p hats equals P. And so you can add that little p hat right there to your subscript for your mu, and it equals 0.4, which is 40% orange. For the standard deviation, there's a little bit more involved with the formula, but it was square root N times P times 1 minus P all over N. So you took the standard deviation you had found and divided it by your sample size. And then let's see, what we could do algebraically is we could just bake the whole thing under the square root and make that N squared. So that way it's still a true statement. Then we can cross off one in here with one in there. And so the standard deviation formula we'll be using from now on is all square root P times 1 minus P over N. So you never have to do the algebra again to find that. You can just use this formula every time. And so these two are going to be very important to us. These are all you have to know. You don't have to know the algebra behind them. I just like to show it for people that do like to know. A couple more things. We still have the large counts condition that says if N times P is at least 10 and N times 1 minus P is at least 10, that it's approximately normal. So that is really important to us as well. And then we did a little algebra down here to find not a little algebra, we did normal calculations to answer this question. And so a couple things here. What we can do for our notation is capital N, the mean equals P, and the standard deviation was square root P 1 minus p over n. So we need that notation to set up a problem. We got our normal curve. Here's our z-score. If we want to put that in a formula, we did our proportion from the sample minus our population proportion over the standard deviation. So it's value minus mean over standard deviation, and the value here would be your 50% or greater. 0.4 was the mean, which was p, and the standard deviation was the square root p1 minus p over n. We use table A to get the answer. So it's a lot of red notes today. Take a minute, make sure you got them all down and that you kind of understand them. And then we'll go to the back where we have even more notes to take. So we're just going to put it all together in one place on the back. Okay, so I want you guys to get all this copied down. A couple things about it before you pause me is that proportions are for categorical variables, so that's going to be like something really important that we want to highlight there. And then we use the symbols that we use are so important. The population proportion, remember that's called a parameter, and that is p. And the sample proportion is called a statistic, and that's p with a little hat on it. And I do have a p with a hat on it, so I got to find it so I can wear it. We have our mean and standard deviation formulas. We have our 10% condition that we need to check when we're sampling without replacement to use the standard deviation formula. That's it ties back to binomial. And then our shape's approximately normal when you have this condition met. And to calculate probabilities, we use the normal curve with our z-score. Notice how my work for number 12, I didn't do the second normal curve, and we're going to stop doing that. We had to do that first semester to get you used to everything, and now you can just draw one normal curve with those problems. All right, now try to check your understanding, and then I will unpause this to go over the answer and show you what I got, and you guys can then go to Canvas to continue the rest of your work. Okay, so here's what I got. Pause it to check through. One thing I didn't do is we need to check 10% to use the standard deviation formula. And so we need to say 50 is less than 10% of all Whovillians. And so that is true because 10%, I need Lorian out of room, but let's do it up here. 50 is less than 10% of 20,000. So 50 is in fact less than 2,000. So we forgot to check that before. And now you can see the rest of these answers. If you have any questions, please don't hesitate to ask. So hopefully you see how it all comes together. Notice I'm not drawing my normal curves with the z-score on there anymore, so we can kind of relax on that rule that we were using and only draw one normal curve now to make these problems go a little faster. Totally fine. And I hope you guys have a great day. Thank you so much. Please reach out if you have any questions.